Hey everyone, welcome back to Stack Lessons. Got 20 fresh questions for you today, focused on chunking architecture, gateway guardrails, and search fusion. Read along, hit pause if you need to, and use the 10-second timer to lock in your answer. Let's go. Now, question 1. Let the constraints drive the choice. A generative AI engineer at Barcliff Solutions has deployed a shared LLM endpoint through AI Gateway that multiple internal teams access simultaneously. The data engineering team runs overnight batch summarization jobs that consume the endpoint's entire token budget for hours at a time, causing latency spikes and failures for the customer service team that uses the same endpoint for real-time queries. What is the most appropriate solution to this problem? Select one. Review the answer choices on screen. The correct answer is option A. A second endpoint fixes the symptom but misses the lever. AI Gateway supports rate limiting at the endpoint, user, and group level, enabling administrators to cap the queries per minute or tokens per minute that a specific group such as the data engineering team can consume. This directly constrains the batch job's consumption without impacting the customer service team's real-time access and requires no changes to application code. Deploying a second endpoint provides isolation but increases infrastructure cost and requires updating the data engineering team's connection configuration. Inference Tables provide observability into request and response logs, but do not restrict consumption or protect the SLA of concurrent users. Switching billing models affects cost attribution per token, but does not throttle request volume or guarantee latency for other consumers. Now, here comes question 2. A generative AI engineer at Vantage Research is building a RAG application over a collection of lengthy technical reports. During evaluation, they observe that shorter retrieved chunks produce precise semantic matches, but the LLM generates poor quality answers because critical surrounding context is missing. Which retrieval architecture should they implement to resolve this trade-off? Select one. Review the answer choices on screen. The correct answer is option B. Small chunk search, large parents feed the LLM. Parent-child retrieval directly resolves the trade-off between retrieval precision and generation context quality. Small child chunks of approximately 512 tokens are embedded and indexed in the vector store, providing precise semantic matches against user queries. When a child chunk is retrieved, the system fetches its larger parent segment of approximately 2048 tokens and passes that richer context to the LLM. This preserves the precision of small chunk retrieval while ensuring the generative model receives enough surrounding context to produce complete, coherent answers. Switching entirely to large chunks degrades retrieval precision because large embeddings dilute the semantic signal of specific passages and pull in irrelevant content. Semantic chunking improves chunk coherence, but does not solve the context window problem since chunk sizes remain variable, and the model may still receive insufficient context. Reducing overlap to zero removes boundary-spanning context, increasing the risk that information split across chunk edges is lost and compounding the quality problem. Let us keep moving. Question 3. Do not rush the wording. A generative AI engineer at a cybersecurity company is building a threat intelligence platform. Threat data arrives as streaming events, and the company already runs an external pipeline that computes embeddings using a proprietary model and stores them in a delta table. The engineer needs to create an AI search index that consumes those pre-computed embeddings without recomputing them. Which index type should the engineer create? Select one. Review the answer choices on screen. The correct answer is option C. Only direct access accepts pre-built embedding vectors. A direct access index is designed precisely for use cases where an external pipeline already produces the embedding vectors. The engineer uploads or upserts pre-computed embeddings and metadata directly via the REST API or SDK, and Databricks does not re-embed anything. A delta sync index with Databricks managed embeddings would recompute vectors using a Databricks-hosted model, discarding the proprietary embeddings. A delta sync index with an external embedding model endpoint also re-embeds source text via a specified model endpoint at sync time, rather than accepting pre-computed values. Storage-optimized endpoints address horizontal scale for very large indexes, but do not change how embeddings are supplied to the index. Time for another one. Question 4. The clue is not in the service name. A generative AI engineer is implementing an LLM as judge evaluation framework to score how well chunks retrieved by a RAG pipeline support answers to user questions. The engineer needs to configure the judge's output schema for relevance scoring. Which relevance scale does the built-in Databricks LLM judge use? Select one. Review the answer choices on screen. The correct answer is option B. Built-in judge, 4 values, 0 through 3. The built-in Databricks LLM judge uses a 4-point relevance scale, 0 for not relevant, 1 for partially relevant, 2 for relevant, and 3 for highly relevant. This graded scale captures the degree of relevance rather than treating retrieval as a binary decision, enabling more nuanced evaluation and aligning with the DCG at 10 metric, that also uses a 0 to 3 intensity range. A binary 0-1 scale loses information about degrees of relevance and is too coarse to distinguish between partially useful and fully on-topic chunks. A 3-point scale starting at 1 has no value representing completely irrelevant documents, leaving a gap in the scoring schema. A 5-point Likert scale is not the schema used by Databricks built-in judges, and would require custom scorer configuration that departs from the platform's native evaluation framework. Ready. Question 5. Track every qualifier. A generative AI engineer at Northwind Healthcare is deploying a patient inquiry assistant through an AI gateway endpoint. Compliance requirements mandate that personally identifiable information such as email addresses, phone numbers, and social security numbers must never be transmitted to the underlying language model. Which AI gateway guardrail configuration satisfies this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Blocking stops the payload before the model ever sees it. PII detection in blocking mode intercepts requests at the gateway layer and rejects any payload containing recognized PII patterns, including email addresses, phone numbers, and social security numbers, before forwarding the request to the underlying model. This is a preventive control that guarantees the model never receives the sensitive data, directly satisfying the compliance mandate. Safety filters target harmful content categories such as hate speech and violence. They do not identify or block personal data fields. Rate-limiting controls request frequency and provides no PII-specific protection whatsoever. Traffic tracking is a monitoring tool that logs data after requests are processed. It documents that PII was sent but does nothing to prevent it from reaching the model. First 5 questions hit 3 control surfaces: AI gateway group level rate limiting, the direct access index for pre-built vectors, and PII blocking at the gateway layer, all requiring precise feature identification over general reasoning. Ready. Question 6. Wording first, memory second. A generative AI engineer at Fairview Research is building a document similarity system using Databricks AI Search. Their embedding model produces unit-normalized vectors, and the team requires that similarity scores reflect cosine similarity rather than Euclidean proximity. What must they do to achieve cosine similarity behavior in AI Search? Select one. Review the answer choices on screen. The correct answer is option B. The words unit normalized quietly change the entire answer. Databricks AI Search uses the hierarchical navigable small world algorithm with L2 Euclidean distance as its fixed distance metric. There is no parameter to change the metric to cosine. However, when two vectors are both unit normalized, cosine similarity and L2 distance produce equivalent result rankings, because cosine similarity between unit vectors equals 1 minus half the squared L2 distance, meaning the ordering of retrieved documents is identical under both metrics. Pre-normalizing embeddings to unit length before insertion therefore achieves cosine similarity semantics without any configuration change. AI search does not expose a distance underscore metric parameter for index creation. L2 is the only available metric and cannot be overridden. There is no normalize underscore embeddings flag in endpoint configuration. HNSW is the approximate nearest neighbor algorithm and is not interchangeable with a dot product computation. No dot product algorithm option exists in AI search. This question has a sneaky math insight that trips up nearly everyone. Let's break it down. Imagine 50,000 research papers as embeddings. You want cosine similarity for retrieval, but Databricks AI Search only uses one distance metric, L2 Euclidean, no parameter to change it. Here's the math trick. When every vector has magnitude 1.0, we call it unit normalized. At that point, cosine similarity and L2 distance produce the same ranking. The formula: cosine equals 1 minus half the squared L2 distance. Pre-normalize your embeddings before inserting. Options C and D invent config flags that don't exist. No distance underscore metric parameter, no normalize underscore embeddings flag. That's the trap. The answer rewards knowing the math, not memorizing menus. Ready? Let's get into question 7. A data science team at Litware has trained a custom text classification model using scikit-learn, and wants to deploy it as a real-time REST API endpoint on Databricks Model Serving. Which sequence of steps follows the recommended Databricks production workflow? Select one. Review the answer choices on screen. The correct answer is option A. Log it, register it, serve it, in that order only. The recommended Databricks workflow for deploying a custom model to model serving is to log the trained model with mlflow.sklearn.log_model during or after training, register it in the MLflow model registry backed by Unity Catalog, and then create a model serving endpoint pointing to the specific registered version. This workflow provides versioning, alias management, governance, and a reproducible deployment path. Saving the model as a raw pickle file to DBFS bypasses MLflow tracking entirely and is not supported by model serving endpoints, which require models logged through LLflow. Deploying directly from an experiment run artifact without registering is possible in some workflows, but skips the model registry, removing version history, alias promotion, and Unity Catalog access controls that are part of the recommended production workflow. Unity Catalog does not automatically generate REST serving endpoints when a model is registered through the UI. A separate model serving endpoint configuration step is always required. Let us switch gears. Slow down for question 8. A generative AI engineer at Irongate Financial is configuring Databricks AI Search for a knowledge base application. Users frequently combine precise regulatory identifiers like Basel III Article 92 with broader conceptual queries like capital adequacy requirements. The team enables hybrid search, which runs BM25 keyword matching and HNSW semantic similarity in parallel. Which algorithm does AI search use to combine the two ranked result lists into a single unified ranking? Select one. Review the answer choices on screen. The correct answer is option D. RRF converts rank positions into reciprocal scores. Reciprocal Rank Fusion, RRF, is the algorithm Databricks AI search uses to combine ranked result lists from keyword-based BM25 and semantic HNSW searches into a single unified ranking. RRF works by converting each item's rank position into a reciprocal score and summing contributions across both lists, controlled by the RRF_param parameter, default 60. This approach is robust to score scale differences between the two modalities and preserves items that rank highly in either component. Cosine similarity averaging conflates dissimilar relevance signals and is not used for list merging. L2 normalization is a pre-processing step applied to embedding vectors before indexing, not a technique for combining ranked lists. Multiplicative fusion would eliminate any document that ranks poorly in one of the two components, reducing recall for queries that only benefit from one search modality. Let's pause here. The fusion algorithm question is trickier than it looks, and easy to get wrong. Imagine two judges scoring the same baking contest, one rates out of 100, the other out of 10. Average those raw scores and the first judge dominates. That's the problem with score-based fusion. BM25, the keyword matching engine, and HNSW, the vector similarity engine, produce scores on totally different scales. Multiply them and a weak score from one kills the result. Reciprocal Rank Fusion, RRF, sidesteps this. It converts each result's rank position into a score, 1 divided by rank plus 60. That 60 is the RRF_param, and it controls how much top ranks dominate. A document ranked third by keywords and fifth by semantics still earns a strong score. The distractors all rely on raw scores. RRF works on ranks, not numbers. That's the trap. Let us switch gears. Let's handle question 9. Quick check. A generative AI engineer at Stratford Media is investigating latency spikes in their model serving endpoint. They enabled Inference Tables on the endpoint 1 week ago, and now want to identify which specific requests took the longest to complete so they can correlate processing time with request content. Which inference table column should they sort by to isolate the slowest requests? Select one. Review the answer choices on screen. The correct answer is option A. Duration lives in one column. Find it by name. The execution_time_ms column in an inference table records the wall clock milliseconds taken to process each individual request from receipt to response. Sorting by this column in descending order directly surfaces the slowest requests, allowing the engineer to examine their content and identify patterns. The status_code column records the HTTP response code, which distinguishes successes from failures, but carries no information about how long a successful or failed request took. The timestamp_ms column records the time a request arrived, which is useful for identifying when latency spikes occurred chronologically, but does not measure the duration of individual requests. The sampling_fraction column records the configured capture rate for the inference table and holds a constant scalar value rather than a per-request performance measurement. Keep your focus here. Question 10. Convert the story into selection criteria. A generative AI engineer at Caldwell Analytics is building a RAG assistant for a retail analytics team. Analysts ask natural language questions about quarterly sales figures stored in structured delta tables in Unity Catalog, as well as questions about competitive strategy described in unstructured internal reports and presentations. How should the retrieval approach differ for these two data types? Select one. Review the answer choices on screen. The correct answer is option D. SQL for numbers, vectors for meaning, never swap them. RAG pipelines handle structured and unstructured data through fundamentally different retrieval mechanisms that match the nature of each data type. Unstructured documents such as presentations and reports are chunked, embedded, and stored in a vector index where semantic similarity search retrieves relevant passages. Structured sales data in Delta tables is best queried through a SQL interface, where precise aggregations, filters, and joins produce accurate numerical results against the tabular schema, rather than approximate similarity matches. Embedding both types in a vector index loses the numerical precision and relational semantics that SQL operations preserve for analytics data. A vector search for last quarter's revenue will surface semantically related text rather than compute an accurate figure. Exporting structured tables as JSON and treating them as text chunks introduces serialization errors and destroys query efficiency for numerical calculations. Converting unstructured documents to CSV forces rich textual content into a tabular structure that discards semantic meaning and prevents effective similarity retrieval. Questions 6 through 10 exposed a math equivalence trap, a mandatory three-step sequence, a specific fusion algorithm name, and a single-column lookup, all rewarding exact knowledge over general intuition about how Databricks internals work. All right, question 11. Check whether it asks what or why. A generative AI engineer is configuring an LLM as judge evaluation in MLflow to score retrieval relevance for a RAG application. The judge assigns a numeric score to each retrieved document. A document that directly and comprehensively addresses the user's query with no irrelevant information should receive the maximum possible score. What is that maximum value on MLflow's built-in relevance scoring scale? Select one. Review the answer choices on screen. The correct answer is option D. Maximum and built-in are both load-bearing words here. MLflow's built-in LLM as judge relevance scorer uses a 4-point scale ranging from 0 to 3. A score of 0 indicates the document is not relevant, 1 indicates partial relevance, 2 indicates the document is relevant, and 3 indicates the document is highly relevant and comprehensively addresses the user's need. A document that fully and directly answers the query with no irrelevant content therefore receives a score of 3. MLflow does not use a 0.0 to 1.0 probability scale, a 1 to 5 Likert scale, or a 0 to 10 scale for its built-in relevance evaluation. Okay, question 12. Picture the scenario first. A generative AI engineer at Conteso Life is evaluating a RAG application built for an insurance claims processing team. Standard correctness and relevance metrics are insufficient because the evaluation requires domain-specific checks, for example, verifying that a generated response correctly identifies which policy clause applies to a described claim scenario. Which evaluation approach is most appropriate? Select one. Review the answer choices on screen. The correct answer is option D. Built-in judges cannot read an insurance policy clause. When evaluation requires domain-specific reasoning, such as determining whether a generated response correctly applies an insurance policy clause, a custom LLM judge with a domain-specific rubric is the most appropriate approach. Custom judges extend the built-in judge framework by supplying evaluation criteria tailored to the subject matter, enabling the judge to apply the same nuanced reasoning a domain expert would. Built-in judges cover general criteria like relevance, groundedness, and safety, but have no knowledge of insurance clause mapping and would produce unreliable scores for this specialized check. Code-based scorers using regular expressions can detect the presence of clause identifiers as a coarse signal, but cannot reason about whether a clause was correctly applied to the described scenario. NDCG at K measures ranking quality of retrieved documents and is a retrieval metric. It does not assess the correctness of generated responses. All right, question 13. Wording first, memory second. A generative AI engineer needs to register a production-ready intent classification model in Unity Catalog on Databricks. The team has organized their workspace with a catalog named prod_catalog, a schema named NLP_models, and wants the model registered under the name customer_intent_v2. What is the correct fully qualified model name to use during registration? Select 1. Review the answer choices on screen. The correct answer is option D. Catalog.schema.model, 3 dots, 3 levels. Unity Catalog uses a 3-level namespace where all objects are identified by catalog, schema, and object names separated by dots in the form catalog.schema.object. The fully qualified name prod_catalog.nlp_models.customer_intent_v2 correctly places the model within its organizational hierarchy, and is the format expected by MLflow when registering to the Unity Catalog registry, which is the default registry in MLflow 3. The /separated format is used in file system paths and is not valid for Unity Catalog object names. Double colons are not a recognized separator in the Unity Catalog naming convention. Appending the catalog with an @ has no meaning in Unity Catalog object identification and would cause registration to fail. Here we go. Question 14. Pay attention to what is really asked. A generative AI engineer at Viridia Publishing is building a research paper knowledge base where documents cover multiple topics with significant shifts between sections. They need a chunking strategy that respects natural topic transitions rather than arbitrary character counts. A colleague cautions that their chosen strategy will substantially increase pre-processing time at indexing. Which chunking strategy are they planning to use, and what is its defining characteristic? Select 1. Review the answer choices on screen. The correct answer is option A. The colleague's caution is pointing straight at the answer. Semantic chunking groups text by embedding adjacent sentences and measuring their vector similarity, keeping passages with closely related meaning in the same chunk while splitting at points where topic similarity drops. This produces highly coherent segments that respect natural topic transitions, exactly what research papers with complex section structures require. The significant trade-off is computational cost. Embedding every sentence to identify cluster boundaries is far more expensive than character counting or separator-based splitting. Fixed size and recursive splitting are much faster but cannot detect semantic boundaries. Context-aware chunking can also identify structural boundaries, but relies on document formatting rules rather than embedding-based similarity measurement. Let's slow down on this one. Picking a chunking strategy depends on what boundaries you actually need. Imagine you're splitting 500 research papers into chunks for a knowledge base. Some papers jump from methodology to results to ethics in 3 pages. How do you keep related ideas together? That's the chunking choice this question tests. Ask, do chunks need to follow topic meaning, or document structure, or neither? If meaning is the signal, that's semantic chunking. It embeds every sentence and measures similarity to find where topics shift. It's precise but slow. If headers and formatting mark boundaries, context-aware splitting fits better. If speed is king and coherence can be imperfect, recursive or fixed-size splitting wins. The exam tests whether you know the cost. Semantic chunking embeds every single sentence, and that's why pre-processing time explodes. Okay, let's get into question 15. A generative AI engineer at Tailspin Toys has deployed a product recommendation model that relies on features pre-computed from several upstream delta tables. The data governance team requires full visibility into which source tables contributed to the features used by the model, and how data flowed through transformation steps to the deployed endpoint. Which Databricks capability provides this end-to-end feature lineage? Select 1. Review the answer choices on screen. The correct answer is option B. Unity Catalog owns the full end-to-end lineage graph. Unity Catalog provides centralized data governance and end-to-end lineage tracking across the Databricks platform. For feature-based machine learning workflows, Unity Catalog traces the origin of features from their source delta tables through any intermediate transformations to the feature tables and ultimately to the models that consume them. This lineage graph allows the governance team to identify exactly which upstream data influenced a deployed model, supporting compliance audits, debugging, and change impact analysis. Inference Tables log the live requests and responses of deployed endpoints, capturing production inference behavior rather than the data lineage of how features were computed upstream. MLflow Experiment Tracking records parameters, metrics, and artifacts during training runs, but does not provide lineage from source tables to features. AI Search indexes vector embeddings of content for semantic retrieval and has no governance or lineage tracking role in the feature store. Questions 11 through 15 retested the 0 to 3 scale, exposed the hard ceiling of built-in judges, required Unity Catalog notation, named semantic chunking's compute cost, and confirmed Unity Catalog as the sole lineage owner. Next up, question 16. Watch for must, most, least, or except. A generative AI engineer at Litware Insurance is deploying a claims processing assistant through Databricks AI Gateway. The compliance team requires that customer social security numbers, email addresses, and phone numbers must never be forwarded to the LLM or appear in responses, but the request itself should still be processed rather than rejected outright. Which AI gateway feature should the engineer configure? Select one. Review the answer choices on screen. The correct answer is option C. Processed rather than rejected changes the required feature entirely. PII detection and redaction identifies sensitive identifiers such as social security numbers, email addresses, and phone numbers and replaces them with neutral placeholders before the request is forwarded to the model and before the response is returned to the caller. The request is still processed end-to-end, satisfying the compliance requirement without disrupting the agent workflow. Safety filters are designed to block requests containing hate speech, violence, or other harmful content categories. They reject the entire request rather than redacting specific fields within it. Rate limiting restricts how many requests a user or group can submit per unit of time, and has no effect on the content of individual requests that are allowed through. Traffic splitting routes a fraction of requests to different model endpoints, which addresses load distribution or A/B testing scenarios, not the removal of PII from request payloads. Let's slow down here. The difference between block and redact is exactly what the exam tests. Imagine a claims agent who blacks out a social security number before passing a form up the chain. The claim still gets processed. The sensitive part is just gone. Two phrases in this stem are doing all the work. Must never be forwarded means mask it, not block it. Processed rather than rejected rules out safety filters, which shred the whole request. PII redaction, personal data masking, swaps a real SSN, say 078051120, for a placeholder. Then it forwards the clean request to the model. Responses get scrubbed too, so nothing leaks back. Block means reject. Redact means clean and continue. The exam rewards knowing the difference. Next up, question 17. Ignore details that do not change the decision. A generative AI engineer at Saltmarsh Health is evaluating the retrieval component of a medical RAG system. For patient safety reasons, it is critical that the system retrieves all relevant clinical guidelines for a given query, even if some non-relevant documents are also returned. Which retrieval metric best captures this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Missing any guideline could harm a patient, Recall wins. Recall at K measures the fraction of all known relevant documents that are present in the top K retrieved results. When completeness is the overriding priority, as it is in medical applications where missing a relevant clinical guideline could harm a patient, recall is the appropriate primary metric because it directly penalizes the system for omitting relevant documents, regardless of how many irrelevant ones are also returned. Precision at K measures what fraction of retrieved documents are relevant, and is the right metric when false positives are costly, not when false negatives are the primary concern. NDCG at K and DCG at 10 both reward correct ranking order and relevance intensity, making them valuable for comparing overall retrieval quality, but they are secondary considerations when the governing requirement is that no relevant document should be missed. Next up, this is question 18. A generative AI engineer at Kessler Research is building a RAG application over a corpus of dense technical manuals. Evaluation shows that chunking documents into 512 token segments produces excellent retrieval precision. The most relevant passages reliably appear in top results. However, the LLM consistently generates incomplete answers because individual 512 token chunks lack sufficient surrounding context for coherent reasoning. The engineer wants to preserve retrieval precision while supplying richer context to the LLM. Which strategy should they implement? Select one. Review the answer choices on screen. The correct answer is option B. Large chunks with overlap sounds smart but kills precision. Parent-child retrieval resolves the tension between retrieval precision and generation quality by decoupling the two concerns. Small chunks are used for search because their focused content matches user queries precisely. Once the relevant small chunks are identified, the system retrieves their larger parent segments and passes those to the LLM, providing the surrounding context needed for complete answers. Increasing chunk size to 2048 tokens with high overlap degrades retrieval precision, because larger chunks are harder to match against specific queries, sacrificing the precision advantage the current 512 token chunks already deliver. Semantic chunking produces topic-coherent boundaries, but does not guarantee the same retrieval precision as small fixed chunks, and the resulting segments may still be insufficient to give the LLM full contextual reasoning material. Disabling chunking and relying on a large context window model is expensive, can introduce irrelevant content that confuses generation, and abandons the structured retrieval quality already achieved. Let us keep moving. Question 19. Classic exam trap. A generative AI engineer is reviewing inference table logs for a document summarization endpoint and finds that some requests are missing even though the endpoint returned responses. Investigation reveals the missing requests involved very large legal documents and requests that received HTTP 429 status codes due to rate limiting. Which two inference table limitations explain the missing records? Select 2. Review the answer choices on screen. The correct answers are option B and option C. 2 documented limits, payload ceiling and error code capture gaps. Inference tables have 2 documented limitations that explain the missing records in this scenario. Payloads exceeding 10 MB are not logged regardless of endpoint response, which accounts for the missing large legal document requests. HTTP 429, too many requests. Status codes fall into the category of error responses that may not be captured, alongside 401, 403, and 500 errors, which accounts for the missing rate-limited requests. Inference tables capture all requests reaching the model serving endpoint regardless of whether they originate inside or outside the Databricks workspace. Records become available approximately 1 hour after the endpoint interaction due to propagation latency, but this is not a manual flush requirement. The sampling_fraction parameter accepts values between 0 and 1, and proportionally reduces how many requests are sampled, it does not create a complete logging cutoff at any threshold. This one trips people up. Let's nail down exactly what inference tables do and don't log. Imagine a surveillance camera that cuts out whenever something is too big or gets blocked at the door. Inference tables work the same way. Two types of requests simply vanish. First, any payload over 10 MB is never logged. Not even a null row. Say a law firm sends a 100-page merger agreement to your summarization endpoint. Gone. Second, HTTP 429 responses, the "you are going too fast" replies, may also be skipped. The trap answers point at three wrong causes. External API calls are logged. No workspace restriction. The 1-hour wait is automatic propagation, not a manual flush. And sampling _ fraction is a read-only number Databricks sets under load. You can't configure it. B and C are your answers. Let us keep moving. Question 20. Look for the constraint that matters. A startup called Fenwick Analytics is building a dual-purpose internal tool. One workflow generates Python and SQL code for data analysts, and a second workflow produces one-page executive summaries from lengthy financial audit reports. Quality is the primary objective. Which model assignment best fits both workflows? Select one. Review the answer choices on screen. The correct answer is option D. BGE large produces vectors only. It generates absolutely nothing. Code Llama 34B is purpose-built for generating Python and SQL across multiple programming languages, making it the optimal model for the analyst code workflow when quality is the priority. Claude Sonnet 4 is a high-quality generative model with strong summarization capabilities, well-suited for condensing lengthy financial audit text into concise executive briefs. Llama 3.370b Instruct is a capable general-purpose model, but lacks the specialized code training that Code Llama provides, making it a lower-quality choice for the code generation task. BGE Large is an embedding model that produces fixed-dimensional vectors for retrieval and similarity search. It generates no text output whatsoever, and cannot perform code generation or document summarization in either workflow. 3 takeaways from this session. First, parent-child retrieval separates index precision from LLM context width at generation time. Second, AI Gateway enforces PII compliance preventively, blocking rejects requests, redaction processes them sanitized. Third, unit-normalized embeddings make L2 and cosine rankings equivalent in AI search without any configuration change. The patterns in this set, decoupled retrieval, preventive guardrails, and rank fusion math, are the connective tissue of every production RAG deployment on Databricks. Nail these and you're not just prepared for the exam, you're prepared for the job.